Section. Introduction. In this paper, we introduce Mixtral 8x7b, a unique model that uses a sparse mixture of experts, SMOE, with open weights. This model is available under the Apache 2.0 license. Mixtral outperforms other models like Llama 270b and GPT 3.5 in most benchmarks. The unique feature of Mixtral is that it only uses a portion of its parameters for each token, which allows it to process data faster at low batch sizes and more efficiently at large batch sizes. Mixtral is a network that uses a sparse mixture of experts. It's a decoder-only model where the feedforward block selects from 8 different groups of parameters. For each layer and each token, a router network chooses 2 of these groups, known as experts, to process the token and combine their outputs. This method increases the number of parameters in a model while controlling cost and latency, as the model only uses a fraction of the total set of parameters per token. We pre-train Mixtral with multilingual data using a context size of 32K tokens. It either matches or exceeds the performance of Llama 270b and GPT 3.5 over several benchmarks. Mixtral shows superior capabilities in mathematics, code generation, and tasks that require multilingual understanding, significantly outperforming Llama 270b in these domains. We also introduce Mixtral 8x7b Instruct, a chat model fine-tuned to follow instructions using supervised fine-tuning and direct preference optimization. This model outperforms GPT 3.5 Turbo, Claude 2.1, Gemini Pro, and Llama 270b, chat model on human evaluation benchmarks. Mixtral Instruct also demonstrates reduced biases and a more balanced sentiment profile in benchmarks such as Barbecue and Bold. Mixtral 8x7b and Mixtral 8x7b Instruct are both released under the Apache 2.0 license, free for academic and commercial usage. We have also made changes to the VLLM project to allow the community to run Mixtral with a fully open-source stack. This includes integrating Megablocks CUDA kernels for efficient inference and allowing the deployment of VLLM endpoints on any instance in the cloud. Mixtral is based on a transformer architecture and uses the same modifications as described in previous works, with the notable exceptions that Mixtral supports a fully dense context length of 32K tokens, and the feedforward blocks are replaced by mixture of expert layers. The output of the mixture of experts module for a given input is determined by the weighted sum of the outputs of the expert networks, where the weights are given by the gating network's output. If the gating vector is sparse, we can avoid computing the outputs of experts whose gates are 0. We use a simple and performant method of implementing this by taking the softmax over the top k logits of a linear layer. The number of experts used per token, denoted by k, is a hyperparameter that modulates the amount of compute used to process each token. If one increases the number of experts while keeping the number of parameters used for processing an individual token fixed, one can increase the model's parameter count while keeping its computational cost effectively constant. Mo layers can be run efficiently on single GPUs with high-performance specialized kernels. For example, Megablocks casts the feed-forward network, FFN, operations of the Mo layer as large sparse matrix multiplications, significantly enhancing the execution speed and naturally handling cases where different experts get a variable number of tokens assigned to them. In a transformer model, the Mo layer is applied independently per token and replaces the feed-forward, FFN, subblock of the transformer block. For Mixtral, we use the same SWI-GLUE architecture as the expert function and set the number of experts to 2. This means each token is routed to 2 SWI-GLUE subblocks with different sets of weights. This formulation is similar to the GS-hard architecture, with the exceptions that we replace all FFN subblocks by Mo layers while GS-hard replaces every other block, and that GS-hard uses a more elaborate gating strategy for the second expert assigned to each token. Section Summary. Mixtral 8x7b is a sparse mixture of experts model that outperforms Llama 270b and GPT 3.5 on various benchmarks. It uses a subset of parameters for each token, allowing for faster inference at low batch sizes and higher throughput at large batch sizes. The model is based on a transformer architecture and employs a mixture of experts layer, where the output is determined by the weighted sum of expert networks' outputs. Section. Results. We've compared our model, Mixtral, with another model called Llama, using a variety of tasks to measure their performance. These tasks include common sense reasoning, world knowledge, reading comprehension, math, and coding. We also used popular aggregated results for comparison. In our tests, Mixtral outperformed Llama in most areas, particularly in coding and math. We also found that Mixtral was more efficient, using fewer active parameters for each token, which means it's less computationally expensive. However, we didn't take into account memory costs and hardware utilization in this comparison. We also compared Mixtral with Llama and GPT 3.5, another model. Mixtral performed similarly or better than these two models, even though it has a smaller capacity. We did notice some differences in our evaluation methods compared to those reported in the Llama paper. For example, we used a hand-verified subset for one of the benchmarks, and we didn't provide Wikipedia context for another. We also tested Mixtral's performance with multilingual data and found that it performed well in multiple languages while maintaining high accuracy in English. To test Mixtral's ability to handle long contexts, we used a task that measures the model's ability to retrieve a passkey inserted randomly in a long prompt. Mixtral was able to retrieve the passkey with 100% accuracy, regardless of the context length or the position of the passkey in the sequence. Finally, we tested Mixtral and Llama on bias benchmarks to identify any potential flaws. These benchmarks measure social biases in 9 different categories. We found that Mixtral displayed less bias than Llama on these benchmarks. Section Summary. The results show that Mixtral outperforms Llama in various benchmarks, particularly in code and mathematics tasks, despite having fewer active parameters. Mixtral also performs similarly or better than Llama 270B and GPT 3.5 in terms of capacity and multilingual capabilities. Additionally, Mixtral exhibits less bias in the bias benchmark for QA and bias in open-ended language generation dataset compared to Llama 2. Section. Instruction Fine-Tuning. We've developed a model called Mixtral Instruct, which we've trained using a 2-step process. First, we used supervised fine-tuning, SFT, on a dataset of instructions. Then, we applied direct preference optimization, DPO, on a dataset that pairs feedback. The result? Mixtral Instruct achieved a score of 8.30 on the MT bench, making it the top-performing open weights model as of December 2023. Independent evaluations by LMSY showed that Mixtral Instruct outperformed other models like GPT 3.5 Turbo, Gemini Pro, Claude 2.1, and Llama 270B Chat. We also conducted an analysis on how the model chooses experts during its operation. We were curious to see if, during training, certain experts became specialized in specific areas like mathematics, biology, or philosophy. To explore this, we looked at how experts were chosen across different sections of the PILE validation dataset. We didn't find any clear patterns in how experts were assigned based on the topic. For example, the distribution of expert assignment was very similar for academic papers, biology abstracts, and philosophy documents. The only slight difference was seen in DM mathematics, which could be due to the synthetic nature of the dataset and its limited coverage of natural language. Interestingly, we found that the model does show some structured behavior in terms of syntax. For example, words like self in Python and question in English often get routed through the same expert even though they involve multiple tokens. Also, in code, the indentation tokens are always assigned to the same experts. We also noticed that consecutive tokens are often assigned the same experts, suggesting some degree of positional locality in the PILE datasets. This has implications for how we might optimize the model for faster training and inference. For instance, cases with high locality are more likely to cause overuse of certain experts when doing expert parallelism. On the other hand, this locality can be used for caching to improve performance. We provide a more detailed view of these expert frequency across all layers and datasets in the appendix.